Hello, everyone. Today, I'll give a talk entitled Machine Learning Basics for Physicians. And I would like to start with this slide here, where you can see the many successes of machine learning and artificial intelligence, which we have seen over the recent years. Maybe some of them you recognize. For example, here, we have Google DeepMind's AlphaGo, which played against the world champion Lee Sedol, the Asian game of Go, and it actually has beaten the world champion. The painting here in the center of the slide that you can see hasn't been painted by some French or German expressionist in the 30s of the 20th century. This is actually a painting which was generated or hallucinated by a computer. Maybe you've also heard about self-driving cars, or for example, the machine translation, which makes our daily lives easier when learning a foreign language. Also, spam filtering to a big extent is done by the machine learning models, or for example, the recent advancement is also Google DeepMind's AlphaFold, which has been able to predict the tertiary structure of the protein much better than any other model designed by computational biologists. One of the first successes of artificial intelligence and machine learning was, by the way, recognizing the digits in the Soviet postal code. So they were written in this interesting, you had to write them in this interesting font for the automatic system to be able to recognize these digits automatically using machine learning. So you might ask yourself, although all of this is interesting, but why should I care about the machine learning? And why does machine learning maybe need me as a physician or clinician or somebody from the medical field? And here I will try to explain to you what is the relationship between the two fields a little bit. So we have, of course, the world of the machine learning research on the one island, and on the other one, we have the world of diverse and interesting and challenging clinical applications. Machine learning research consists of really different folks, including computer scientists, statisticians, mathematicians, and physicists. And many of us work on developing really complex and mathematically difficult models and methods, but we are interested in, of course, trying these methods out in practice. And we haven't applied them yet, and some of them just remain on the level of theoretical research. On the other hand, there are clinical applications which are driven and solved by clinicians, physicians, medical researchers, and biologists. And often they face the issue that they have really complex data sets consisting, for example, of time series data or images or some other more complex data types that cannot be analyzed with conventional statistical tools. So I would say that there is a clear basis for a friendship in a sense that one community has the methods and another community has the data sets that these methods could be applied on. However, there are many gaps between the two communities. In particular, I think it is difficult to establish interdisciplinary collaborations because of terminological barriers and general lack of awareness about the problems that arise in these two communities. So today, we'll try to learn about the basics of machine learning, and we'll try to bridge this gap maybe at least a little bit. So what we'll talk about today is we'll try to establish some clarity over the terminology. In particular, we'll understand what are differences between machine learning, statistics, and artificial intelligence. We'll try to understand what actually machine learning as a discipline is trying to solve, and we'll study its fundamental problems. We'll then talk a little bit about supervised versus unsupervised learning, which are two types of machine learning. Then we'll learn what is different between classification and regression. And we will consider a typical pipeline of the supervised machine learning applications. We'll also study the topic which is very important to machine learning and is the holy grail of machine learning, which is generalization. And then we'll learn about two very popular and still widely applied machine learning algorithms, which are called tree-based learning and random forests. So first, let's settle with the terminology, and often when I talk to my biology or medical collaborators, or generally collaborators from the other fields, I feel that they are sometimes confused about what machine learning is and what is its relationship with the other fields such as statistics and artificial intelligence. So let's first look at the statistical modeling versus machine learning. What is the difference? Maybe many of you have taken, for example, Introduction to Statistics course in your university when receiving your degree, and you are of course familiar with statistical modeling to some extent. Generally, I would say that statistical modeling has an inherently different goal. The task of statistical modeling is to perform inference, that is to identify certain important properties of the system that you are trying to model. For example, if you think of medical applications, you could think of estimating a treatment effect in a randomized controlled trial, or for example, estimating a correlation between some prognostic factor and some outcome. Statistical modeling usually is very explicit about sources of uncertainty. In general, it specifies a very mathematical probabilistic model of the data. For example, be it variability across the clinical centers or just random effects that are produced by sampling from different patients and so on. And then statistical modeling tends to, as a result of its probabilistic treatment of the data, make rather strict assumptions about the nature of the data. For example, it often assumes linear associations, for example, like in linear regression or logistic regression, or additivity of effects. That is, if I apply two treatments to the patient, I usually assume that these treatments don't interact, or if they interact, I should model the interaction explicitly. So I have to know about this. Machine learning, on the other hand, focuses extensively on the prediction. It is by nature empirical and algorithmic. It is more part of computer science than statistics. And generally speaking, it works with very general relationships and makes few assumptions. Although the assumptions are still there, but they are not about linearity or additivity. So, but you might ask, and this is probably the most frequent source of confusion, is machine learning versus artificial intelligence. I see a lot of medical articles which in fact do machine learning, but they write something like using AI to do this or using AI to do that. While this is technically correct to say that you use AI when you use machine learning, it sounds a little bit unspecific. Why? Because artificial intelligence is a very broad term describing systems and machines that try to mimic human intelligence. For example, by automating and optimizing tasks often performed by humans. You can think of any task really, like playing chess or diagnosing patients. Machine learning, on the other hand, is much more specific. It is about how we mimic this human intelligence. In particular, machine learning is about designing computer programs that can learn with experience. So basically, one can think of machine learning as being a subset of artificial intelligence. Not every artificial intelligent machine is a machine learning machine, whereas every machine learning application is artificial intelligent. You can also think of surgery versus medicine, where surgery is a very specific subfield of medicine. And this is summarized, of course, graphically in this picture, where you have a big set of artificial intelligence research, and inside of it, somewhere lives machine learning. So now that we understand how machine learning relates to the other disciplines, the question is, what does machine learning do? And what is the main problem of machine learning? So in fact, most machine learning algorithms and approaches out there try to solve what one could call the fundamental learning problem. And here is one possible broad definition of this problem. We say that a computer program learns from experience, denoted by capital letter E, with respect to some class of tasks T and performance measure P, if its performance at tasks in T as measured by P improves with experience E. So this sounds a little bit cryptic and too formal, and to deformalize it, basically what you have is a computer program, and then you have a bunch of experience, which usually is the data that you have observed. You take this data, you put it into the computer program, and you hope that the computer program would improve its performance P at doing some task. And these tasks can be really different. You can do a lot with machine learning. Let us consider one example. And the example is the one from Patricia's and my work, diagnosing appendicitis in pediatric patients admitted to a hospital with abdominal pain. So that's a task. We want to give the diagnosis to a patient with suspected appendicitis. The training experience is about observing the clinical record of patients. And this clinical record may include really different variables, for example, history or clinical examination, laboratory parameters, and ultrasonography. And then the performance measure P is very simple. It's just the percentage of patients that we have correctly diagnosed using our computer program. And schematically, this can be summarized as follows. Here we have our data, which comes in form of demographics, clinical laboratory scoring, ultrasound variables. We put this data into some machine learning model, which does some sort of magic. So that's our computer program. And then it makes a prediction of diagnosis. So in fact, if we look at this learning problem, then a lot of people have worked in machine learning for years. The field has been established, I would say, somewhere in the 70s of the 20th century, and a lot of different subtypes of this learning problem have arisen. There are, generally speaking, two big types of learning problems that we deal with today. These are supervised learning problems and unsupervised learning problems. When you hear supervised and unsupervised, you could think of learning the language with a teacher and learning a language on your own through a book. So supervised learning is like learning a language with a teacher at school. In supervised learning problems, usually we have labeled training samples, which means that every training sample has a label, some value attached to it, like for example, a score or some category. And we would like to learn a function or a model that maps inputs or features to the correct output or the label. More precisely, let's consider an example. So here we have our training data, and let's say our task that we are trying to solve is to be able to recognize the object that is drawn in the picture. And we have our features, which are just pictures. We have a picture of bananas, we have a picture of an apple, and a picture of a dog. And then what's important about supervised learning is that we have some sort of labels. In this case, we have just a written text. Next to a picture of banana, we have it's a banana, or next to a picture of a dog, it's a dog. So then what we do in supervised learning, we take these labeled training samples and we put them into some sort of machine learning model and we learn it. And this machine learning model is just a function which maps features to labels. So it learns to predict the labels on the basis of the features. And then in the future, when I have learned my machine learning model, I can have an unseen data point, and this data point just has the features. It doesn't have a label. And I might ask my machine learning model, what is the label of this data point? And then machine learning model will start to reason in order to derive the prediction. So it will compare this picture of a puppy to a picture of banana it has seen and say, this is not very similar. It's not an apple either, but I think it is rather similar to a dog. So I might as well say it is a dog. And that's how supervised learning works in a simplified manner. And the second type of the problems that we often deal with is the unsupervised learning, which I would say currently is probably the hottest area in machine learning. In unsupervised learning, the task is a bit more subtle and not clearly defined. What we seek is to self-discover certain patterns from the training data without any pre-assigned labels or scores. So in this case, our training data is much messier. Instead of having features and clear labels such as it's a banana or it's a dog, we just have a big bag of features. a lot of drawings and we don't know which drawing corresponds to what. And now we also learn a machine learning model, although we use different algorithms in practice to learn such models. And in the end, what we would hope this model do is discover some patterns on its own. For example, one possible pattern one could discover here is two groups. One group consisting of something like fruit, including pineapple and banana peel and etc. And the other group consisting of one could call animals, dogs and puppies and so on. So in this case, the problem is much more open-ended and it is not really clear what exactly we want to achieve. So you might ask me when to use what types of learning problems are suitable for what types of real data. And here are some examples from the biomedical literature where people have leveraged machine learning to solve or analyze real-world data sets. So here is some examples of the supervised learning problems that you could find. These are things like diagnosing and referring patients with retinal disease based on optical coherence tomography scans, or for example, predicting COVID-19 diagnosis based on the symptoms of a patient, self-reported symptoms, or predicting mortality in cirrhosis patients based on easily scored clinical variables. What is common among these problems is that we have access to labeled data, and usually a lot of it. We have a clear end target that we are trying to predict, and the problem definition is very simple. It sounds like I would like to predict COVID-19 based on the symptoms that I have written down in this questionnaire, and so on. In unsupervised learning, things are a little bit more difficult, as I've mentioned. And here are some examples of the papers. These are things like discovering heart failure phenotypes based on unstructured medical record data, or finding novel subgroups of adult onset diabetes, or identifying groups of slow and rapid decliners among patients at risk of Alzheimer's disease. So in this case, we have data sets where we usually don't have any clear labels. Often our research question is very open-ended. It is often about what can I find in this data set? Is there anything interesting going on? And usually solving unsupervised learning problems results in discovery of novel patterns. Unsupervised learning is tremendously good for the exploratory analysis of the data. So today, we'll pick a simpler problem. We'll try to talk about supervised learning because this is probably the biggest success story of machine learning. Many of the examples that I have shown to you are supervised learning examples. Although a lot of success these days is also coming from leveraging unsupervised learning techniques. So actually, if we look at the supervised learning, then there are two major tasks that supervised machine learning can solve. These are classification and regression. You might have heard word regression a lot in statistics, and basically regression in machine learning is exactly the same as in statistics, but the purpose is a bit different. In statistics, we would like to infer some parameters. In logistic regression or linear regression, in machine learning, we really care only about predicting the label. Although some machine learning techniques can also do inference. So what's the difference between the two types of supervised learning problems? In classification, labels that we have to predict are categorically valued. In other words, they are discrete and typically arranged in disjoint categories, which we call classes. And some examples of labels that we might like to predict is, in case of our drawing example, are apples, bananas, pears. In case of patients, it could be classifying between healthy and sick patient, or between a patient without appendicitis and with appendicitis. Typically, in classification tasks, we do not have any ordering among the classes. In other words, we cannot claim that apple is somehow greater than banana, or banana is worse than an apple or so. That's not the point. These categories are not comparable. It's like comparing apples and oranges. A model that predicts such classes is commonly known in machine learning literature as a classifier. Regression, on the other hand, happens when we try to predict labels that are continuously valued. In other words, they are expressed as real numbers or a subset of real numbers. And some examples are like predicting the price of a house based on its area, or predicting heart rate based on a wearable signal, or predicting Kellgren-Lorentz grade based on the X-ray of a knee. As a result, in regression, labels have natural ordering because we talk about continuously valued labels. For example, we know that the heart rate of 73 is greater than the heart rate of 61. Sometimes the border between these two types of problems is not quite as clear. And generally speaking, I would say, and I would encourage you when you work with statisticians or with machine learners to choose carefully, what do you use, classification or regression? Because different models allow you to do different things and generally tend to pick up slightly different relationships. So choosing between the two approaches is an important step in your statistical modeling or machine learning routine. Okay. So now that we have figured out what types of tasks can we solve with supervised learning, how does supervised learning happen in practice? And in this slide, I would like to schematically introduce to you a typical supervised machine learning pipeline summarized in a very simple manner. So let's say what we are trying to solve is we are trying to predict a class. So we are in a classification problem. And let's say that we have a medical data set which consists of some features, so some explanatory variables that we have observed, such as, for example, patient's age, patient's gender, BMI, etc., etc. And we are trying to predict whether a patient has a certain disease. We have our training data set. So that's the sample that we have collected. And we have here features, of course, and the labels. And the labels are yes or no. Does a patient have a disease or not? And in this case, we have only one patient without a disease, but generally speaking, we would expect data set to be bigger than 12 points. So usually we talk about hundreds of patients or thousands of patients or tens of thousands of patients in some cases. So what we do in supervised learning is that we seek to learn a machine learning model. And to learn this model, we need some sort of learning algorithm. This algorithm is like a recipe which tells us how to extract patterns from the data. And using this algorithm, we extract the model from the data using an inductive type of reasoning. So this step is generally called induction and can be thought of as an induction because we observe many things and we generalize them to something abstract. After that, of course, once we have learned the model, we have it running on our computer. It's usually a program or an equation or something like that. And then sometimes we might also have access to what we call validation data. Validation data is usually another data set, sometimes coming from an external organization, for example, from another hospital, which again consists of similar data points as we have had before, but we haven't trained our model on this validation data set. So what we could do with this validation data set is evaluate the model to understand whether it works. And then by evaluating it on the validation data, we can decide sometimes that the model is inadequate. That, for example, we might need to change something about our pre-processing of the training data, or maybe we need a different learning algorithm. So we might go back to the ground zero again, like in the children's circus game. And this process can go on and on and on again. However, in the end, once we have converged to some learned machine learning model, we would like to, of course, understand whether this model works well. And we have our test data set. Very importantly, this test data set, again, isn't part of our training data. It's some sort of external or just withheld data that we have kept untouched. And in this test data, we don't know what the labels are usually. And what we do is we apply our model using deductive reasoning to these data points to make our final prediction. And usually then when we observe the true labels by, let's say, following up on the patients, we can figure out how good our model in the end is. And write up a good paper, or maybe even start using a new system in the hospital, which would be machine learning based. So you might ask, but what is the kind of big abstract end goal that machine learning is trying to solve? And the holy grail of machine learning is something called generalization. In the end, by performing all of this difficult pipeline, what we want is to learn a model that generalizes well. In other words, a model that can extract the abstract essence of the relationship between the features and labels, and the model that makes really accurate predictions on unseen data. To explain more generally the idea of generalization, here is a small example for you. Let's say we want to be able to recognize trees from the pictures of them. And we want to train a machine learning to do this. And we might have really different trees. The color of foliage might be different. The geographical area from which these trees come might be different as well. So ideally, what we want is that the model would learn some kind of abstract notion of a tree, an average tree, and use this abstract notion to detect the trees in the future. This is kind of an ideal scenario when the model would generalize. Instead of remembering, okay, these types of trees are, fir trees, these types of the trees grow there. Rather, we want some kind of general idea, an abstract idea of what a tree is. In the end, we can evaluate this generalization in terms of generalization error, and this is done on our test set on unseen data. In other words, on the data that the model has not been trained on. And as I already mentioned, this test data needs to be really separate from the training data. And this is known as the commandment of machine learning. You never train on your test data. You keep it separate. Why? Because you want a realistic estimate of your generalization error. If you train on your test data, that's not honest. You're going to get a very optimistic evaluation. Think of a student in the class in the university. Your exam exercises are usually different from the ones you solve in the class. And that's how the lecturer can check your understanding of the abstract concepts that you have learned. Okay, so this is all nice and all, and you might say, but this is a little bit too general. We learn some sort of model, but how can we learn this model? And what is a machine learning algorithm? I don't understand this. And I would like to give you two examples of machine learning algorithms, one of which was invented somewhere in the 80s of the 20th century, and the other one was introduced in 2001. However, despite their rather old age, these algorithms are still very popular in practical applications of machine learning. And even if you open a paper, a medical paper from 2021 using machine learning, you will find these models being used. They're very practical, they work well, and they work with tabular data. So the kind of clinical data that usually hospitals tend to have, which you could put in a table, or electronic health records data as well if you pre-process it slightly. So the first one is called tree-based learning. So I would like to provide some motivation to you. Let's imagine that you are a general practitioner, and let's say you have a patient who phones you and you're on vacation. And patient says, I'm really sick, doctor. I would like a recommendation from you. But you are on vacation and you're not willing to talk too much to your patient. So you're willing to ask only two questions: whether the patient has difficulty breathing and whether they are bleeding. And based on that, you're going to issue a recommendation, whether the patient goes to the hospital or stays at home. This is a very unethical example, but it will work to understand what a tree is. So you may represent your sequential reasoning process about what kind of recommendation to give as a decision tree. And I think you might have seen these decision trees before, because they're often used in medical papers to represent inclusion or exclusion criteria when you create your sample or a cohort. So first you would ask the patient, do they have difficulty breathing? And then let's say if they have difficulty breathing, then they clearly have a problem. So you say, go to the hospital. And that's one class that you're trying to predict. Then, if they don't have difficulty breathing, there is another question that you are willing to ask, and it is, are you bleeding? And if the patient is bleeding, then you again say, go to the hospital. If not, then you say, stay at home. And this structure here, where you successively make decisions, and based on the outcome of these decisions, classify the patient into the two groups, is known as the decision tree. Why is it as a tree? Is because if we flip it, so if we turn it the other way around, it looks like a bush or a tree. So why tree-based learning is generally a useful way to represent classification and to represent classifiers? Well, because in practice, we can learn such decision trees using algorithms from the data. And people have derived many different procedures on how to learn these decision trees. And we can perform classification and regression with the help of these decision trees. Why is this approach called tree-based learning? Well, I have explained is because we can represent our prediction process as a sequence of decisions or splits and visualize it graphically as a tree. Decision tree models really come with many advantages, and some of those are that they are easy to explain to non-machine learning experts. So if you're a machine learning expert working with medical specialists, you can show them the tree and they will understand what is going on. They're easy to visualize and interpret for the clear reasons similar as above. They are easy to apply at prediction time. Unless these trees are really big, you can even apply them to your patients without a computer. So I can print out this decision tree for you and you can use it in the clinical practice. And one could argue that they work in a way that is very similar to human decision making, or at least in the way that we try to represent our decision making. So if you ever watched Bob Ross, I'm not sure, then you might have yourself a happy little tree. He was like a painting teacher who really liked to paint trees on American television back in the 70s, I think. So let's keep things more concrete and let us consider a simple example of tree-based learning to see how it happens in practice. Let's consider a data set which has two classes, which we will denote by blue circles and orange squares. And let's say we have a really simple data set. We only observe two features, X1 and X2. So you can think of, for example, observing patients' age and weight, or I don't know, patient's temperature and age, or whatever. So these are two arbitrary features. And let's say our data set looks like this. So that's what we have observed. We went to the hospital, we made our measurements. We have a very small data set where we have only 5 boxes and quite a few blue circles. And here we have the values of X1 on the ordinate axis and X2 on the abscissa axis. So then we would like to learn a tree. How do we learn a tree? Well, to learn a tree, we need to make some splits or some decisions based on our features. So based on either X1 or X2. And there are efficient ways on how to decide where I make my decisions. But I'll not go into the mathematical details of how it's done, but let's say that I decide to make a decision based on variable X1, and I will consider value W1 of X1. So this is this pink line here, magenta line here. Why is this value good? Well, you will see in a second, why is this a good value to consider? So then I might ask myself a question. Is the value of X1 smaller than W1? Well, if it is smaller than W1, then what happens? Well, actually, in my data set, all of the data points which have X1 smaller than W1 are blue circles. So based on my data, I believe that whichever data point is to the left of the magenta line can be classified as a blue circle. So that's why this is a good line to pick, is because everything to the left of it can be classified as a blue circle. However, and we have gotten rid of half of our data points approximately with this decision. However, if X1 is not smaller than W1, then the picture is slightly more difficult, because to the right of W1 here, we have a mishmash of data points. We have both the boxes and the circles. So I need another decision to make. And the only decision which makes sense in this case is to split or to make the decision based on x2. So I make a decision based on x2 and I consider the value w2 of x2. And then again, I ask myself as a question, is x2 bigger than w2? Well, let's have a look. If x2 is bigger than w2, then this corresponds to the points which are above the green line. And I have gotten rid of the gray points, remember. So everything that is above the green line and is still active is actually an orange square. And that's pretty good. So it means an easy answer for me. If yes, then I can classify this data point as an orange square. If no, then the picture is again very simple. All I have left now are the blue circles. So again, if the answer is no, I classify the data point as a blue circle. And here you go. You have just grown your first decision tree. It's a very simple example with really few data points and only 2 predictors. But you can imagine that such trees can be grown when you have a lot of explanatory variables and when you have a lot of data points. And in fact, this is really fast to do. And even when the borders between your classes, so the decision boundary is very complex. And here is one simple but complex example to an extent. So here you can see again, we have 2 features. This time the different classes are pluses and minuses. But this time the difference is that I don't have such a simple decision boundary. I have a lot of different pockets here. I have minuses here, and then I have pluses, and then I have another island of minuses. So my decision boundary is very complex. I have a complicated relationship going on here. And actually I can use the tree and it will learn this relationship perfectly fine. So here is one example. I'll not go through the details about how it's being done, but you will see iteratively how the tree is grown by a computer program. So we start by splitting our space again into 2 half planes. And to the left, we have some minuses, a lot of minuses and some pluses. To the right, we really have a mishmash. And then we continue to split these rectangles again and again and again until we have reached an area where everything is either a plus or a minus. And the first one we do is in the area A. Everything that is left here is a minus. So we are sure that things that will fall into area A, we believe that they will be a minus as well. For the rest of the areas, we still have to continue splitting. And we do so until we have arrived at many, many small rectangles for which the decision is clear. And that's how you can apply trees to learn even such complex relationships. And you can extend it even further to having more than 2 predictor variables. So there is always a but. In practice, tree-based learning is simple and fast and nice to explain to non-machine learning practitioners, but there exist many disadvantages. And generally, that's why trees are not used as widely anymore. In particular, trees can only represent boundaries between classes that are made up of rectangles. I'll not go into mathematical details why, but in general, this might not work in some data sets very well. So there are many more approaches which are more flexible. Trees generally suffer from having a lot of algorithmic parameters. For example, it can be difficult to decide when to stop growing your tree. This can be a very non-trivial question, and these parameters need to be chosen, which makes them a bit more complicated to apply in practice. And last but not least, probably the main reason why trees don't work so well is that they are quite sensitive to even small changes in the training data. So generally speaking, if your data is noisy, and most of biomedical data is noisy, trees don't work so well. So the question is, can we really improve the trees? Is there anything better? Or maybe can we change them somehow to make them better? And the machine learning community has come up with a good answer. What if we would learn multiple trees? Instead of just having one tree, maybe having many trees is a better idea. And the answer is, it is. In 2001, statistician Leo Breiman, who also worked in machine learning, has proposed another machine learning algorithm that is called random forests. And random forests are built on the success of decision trees. And the idea of random forest is that it consists of many, many decision trees. And a model consisting of many decision trees we call a decision forest. So I will explain what random forests do in a rather simplified manner. There are more technical details to it. However, I think this illustrates the gist or the general idea of it very well. So the idea of random forests is that we grow many trees or capital K trees on the data sets that have been sampled randomly from the original data set. So instead of taking a complete original data set or original training data set, we just sample patients randomly from it and train a new tree on every random sample. This randomness is very important to make the model more robust. And you will see why. I'll try to explain it intuitively, why this works. And then what I do with these K trees is that I aggregate the predictions that these individual trees make to produce the final prediction. For example, if I'm doing regression and let's say I'm predicting the heart rate, I could just take the average of the predictions across the trees. Or if I'm predicting the class of a patient, such as healthy or unhealthy, I might take the majority vote, like in democracy. So what's the intuition? Why does it work? Why is it a good idea? Well, I like to think of random forests, or I like to explain them when I have to explain them for the first time, that it is like in democracy. Think of elections. An individual voter in general is expected to be a well-informed individual. Ideally, they have read the platforms of different political parties and so on, but they might not be an expert on the topic that they are voting on. Let's say we are in a Swiss system where we have to vote on many, many things. So I might be well-informed, but I might not be an expert on the topic. However, because I have many voters and there are many people in Switzerland, and these voters are very diverse, they come from different backgrounds, they come from different cantons. Ideally, I expect that they are diverse enough that this will average out marginal and harmful opinions. And so the diversity in random forests comes from the fact that you take a random sample of your data. And of course, the many voters you have are the many trees. So you can think of every tree as being a single voter in a democratic system. In the last 10, 20 years, I must say that random forests have become really popular and they have been proven to be very successful on tabular and clinical data sets. And they have become really a standard choice for classification when dealing with simpler data sets. So whenever you have a tabular data set, which does not consist of images or time series, random forest is a good go-to model to try first. And here is maybe a more schematic representation of how random forests work, just to make it a little bit more visual. Let's say we have a new data point for which we are trying to make a prediction, which we call instance in machine learning sometimes as well. And let's say we have our random forest model. So what we do is we take this instance, we make a prediction with the first tree of the random forest. So we make our decisions. Then we make a prediction with the second tree, and so on and so forth until we have reached the nth tree, so the last tree that we have. And we have many of those. Every tree, of course, predicts its own class. Let's say we are in classification. So the tree 1 predicts class A, tree 2 predicts class B, and the last tree predicts class B as well. So then we take these classes and we aggregate them by performing, for example, majority voting. So we take the most prevalent vote among those, and in this way, we have our final class, which is our final prediction. So this actually concludes my presentation. We have learned two very interesting learning algorithms. And before we finish, and maybe I'm open to your questions, I'd like to recap what we have learned and how we have tried to bridge the gap. So today we have learned what is the terminological difference between statistics, artificial intelligence, and machine learning. We have learned what is the fundamental problem of machine learning and what general types of problems it is trying to solve. Now you can differentiate between supervised and unsupervised learning problems. You know what makes classification and regression models different. You know what the typical supervised learning pipeline looks like in practice. You know how decision trees and random forests work. So thank you very much for your attention. I would like to say many thanks to Patricia for, again, inviting to this talk, and to Professor Julia Vogt, my supervisor, for sharing and allowing to adapt her slides from the Data Science and Medicine course from ETH Zurich. Thank you very much. So I'm happy to take questions if there are any now.